apologise for that. Which means that I'm not any better prepared to introduce this than you are by reading the slides. So I can tell you that this is a talk about using game analytics to evaluate puzzle design and level progression in a serious game. I'm waiting to find out about it just as you are, so I'm going to hand over now.
All right. So, hello everybody. Thanks a lot for coming to one of the last sessions right after lunch in this building, which is so far from, from where food was served. I'm going to be talking about some work that I did with Drew Hicks, Elizabeth Rowe, and Tiffany Barnes, and a number of other people. And this work, let's see. How to even say, we first met actually at an EDM conference, and they were interested in seeing, what if some of the techniques that we've done in the past on intelligent tutoring data could actually be useful in terms of figuring out what students are doing and learning inside of a game. And so we started that collaboration, and this is one of the works that's coming out of that. And so I guess we can jump right into it. The game that we're going to be talking about is Quantum Spectre. This is an optics puzzle game. So the idea is that the student or the player will use a variety of mirrors in order to bounce these lasers into the correct color configuration. And you can see a little bit that one of them, this one on the bottom, has got two colors on it. That means you have to get both of the lasers there. And the primary, learning objectives, if I mention that or say what the scientific content is going to be the angle of reflection as well as slope. And so those are the things that the students would be tested against. And so the interactions look about like this. So if I use the term interaction, what I mean by that is this is one step of a student solution. So initially, there's nothing there. The laser is in its initial configuration, but then the student places a mirror in one of the positions. So you can see the laser kind of stopped a little bit. It's a little hard to see, but and then you can see that it bends. And so like each step, that's what we're going to consider interaction if I use that term. So there are two groups for this for this study that I'll be talking about once I get to the data. The two groups are, they were given exactly the same game treatment, but the difference was in the way that they were introduced to the game and the way that the content was connected to the game content was connected to the scientific content. So the bridge group, the teachers used game-related examples. So they might show a picture of the game when describing, slope. Or they might ask the students, as part of the discussion in class, how can we use slope in this game in order to figure out, the proper mirror placement. While the game-only group was given, kind of, I guess what you'd say, like the standard lecture on these topics with no direct, ties to the game. But they were also encouraged to play the game. So theoretically, that part would be, equivalent between the classes. And they were, encouraged to do play the game at home for homework. Both groups were. So they shouldn't have been playing it in class, although the teacher might have led them through something by using the game. That was really up to their discretion. So overall, we have 433 students from 29 different classes. And these classes ranged from a couple different grades. Some were maybe a AP grade or something, like a advanced course. And so for the most part, that was balanced. But there's 15 classes for the bridge group, which totaled 175 students, and there are 14 classes for the game-only group. And that ended up being about 258 students. We also have a subset of this, are students who completed a post survey that was asking them about their experience, like how did they feel about certain aspects of the game, what was their perception of their own learning, and stuff like that. So the problem is some players don't complete a lot of these puzzles. So this is kind of similar to the dropout that we've seen through the conference in terms of completion, etc. And it's not particularly even where people tend to quit. And we'll end up seeing that there's even some differences in the groups of the instruction about how long students remain engaged. So our questions are, well, where do they quit? What's the impact of that, and kind of why? So one of the ways that we can kind of explore this type of thing is something called survival analysis. And so that's what we're going to get into in a moment. But even without that, just by plotting the percentage of attempts, this is the total number of students who at least opened the problem, at least looked at it, where we have a log record. And then the bottom is the puzzle levels themselves. So starting at the beginning and going towards the end. And we can just see a really sharp decline at a certain point. And this is a game where you have to complete a level in order to move on to the next one. So we do see something that's a bit of a problem area, or at least an area where something's going on, and so it's worth exploring a little bit more. Also, what's important here is that there's a big difference in that drop-off rate between the two groups. So people who are in the bridge group were less likely to drop out than ones who are in the game group. And this dropout has a really important effect on any other types of evaluations that we would want to do. If we're looking at post-test or any other measures, we now have this biasing effect where some people have stayed in longer than others. And since there's that systematic effect going on, that changes, it's a confounding factor if we're trying to look at some of these post-assessments. And so, like I said, we use survival analysis for a part of this. And so survival analysis gets its name from medical literature. And so the idea is, if you have some type of a treatment, how long do you live? And so that's a little bit morbid, but other names are maybe duration analysis and things like failure time. So you want to see how long maybe a part lasts, how many iterations of use before a door breaks off the hinges, stuff like that. And so this gives us a measure of the likelihood of an event. In this case, the event is stopping the tutor. And so the things that we can answer with survival analysis that are harder to answer with other methods is you can say, how long would it take students to complete the tutor, instead of asking the question of how long did it take people to, and I say tutor, but it's a game or a treatment or whatever. How long would it take? How long did it take people that did complete it? And so that's what happens when you cut out all of the people who didn't get to a certain point. You've changed what you're actually stating in the end to be what about the subset that did make it to this far? What were their time limits? So you have to be a bit careful between that. So like I said, survival analysis, statistical technique. I'm not going to go too much into the actual functions. But the really big takeaway is going to be that we're looking for this probability that at time t the event will happen, and so this basically at if we are doing it in terms of actual time, we might say how likely is it at 62 minutes for someone to to quit. Likewise, if we change the measurement of time to be levels, then we can say at how likely is it for someone to quit after 10 levels? And so it's pretty good at shifting around what you mean by event and what you mean by time. And so, like I said, it's not too important to get in here. One thing I might mention is a hazard function. And so the hazard function really is it's that instantaneous rate of failure. So it'd be at exactly 22 minutes, what's the likelihood of someone dropping out? And you really get the sum of that in order to get up there. The other thing that survival analysis has that's really, really helpful is that it's taking into account the fact that there might be censored data. And so this is the case where if you want to know how long it takes someone to complete the tutor, but people dropped out, this will take into account that that they haven't made it to the end. And so this happens in in medical literature because people maybe stop reporting or something. And so it's nice that it takes that into account. And this helps us address some of the biases that we'd have if we just dropped off those data points. In our case, almost everything's going to be right-censored because we always know when people start. But sometimes we don't know how much longer it would have taken someone to quit if they quit early. And so that's kind of what we're looking for. And one of the things that you'll see, like the most common plot for survival analysis, is Kaplan-Meier plot. And you can see kind of how it does the kind of step look. And so that's kind of a characteristic place. But this is going to be the kind of like the observed probabilities. The other thing I'll talk about a little bit is going to be accelerated failure time. And so I hate to be too complicated with some of these things, but there's a bit of an interpretation difference between the value that you'll get as an output from accelerated failure time than you would from using kind of a standard survival analysis approach. And the main thing is, in accelerated failure time, you're really looking for a direct modifier on the lifetime. So in this case, a really good example is you have humans and you have dogs, and there's a certain amount of time that that they have for a life. And so the direct modifier would be 7 if it was to that, and you would say that, well, a human is expected to live 7 times longer than a dog, or something like that. So in our case, we're going to talk about how much longer students would be engaged in the game than the other. And I find that accelerated failure time and the theta value that you get from that is much easier to interpret. So instead of trying to say the instantaneous failure time at this certain point is this likelihood value, we can actually just say 70% of the other group. So here's the result from plotting the bridge, which is going to be the darker solid line at the top, versus the game-only group. And you can see the kind of red line there. That's going to be the accelerated failure time curve. And this really let us see that there is a significant difference in how long students remain engaged in the game. And this is in terms of minutes. Or actually it's seconds. And so we have more or less we have a significant difference in the amount of time that's spent. And if we want to say get that value for theta of exactly what that means, it turns out it's about 70%. So we would say that people who are in the game-only group only remain engaged or playing the game for 70% of the time that the people in the bridging group did. So there's there's an effect there going on of just from the type of way that the students were introduced to the game. We can do the same thing by level instead, and by doing that, we can kind of find essentially how many levels do we expect one group to complete versus another one. And we start to see this kind of effect where there's still these certain areas where suddenly there's a large drop-off. And so I'll get into why we think that is. Again, I mean, these plots all look really similar. The biggest takeaway, though, is between the two groups, there is, one group is just remaining engaged longer, and then specifically, there's one level, level 21, where the chance of dropping out is much higher for the bridging group or for the game group versus the bridging group. And that ends up being kind of interesting of what is it that's causing people maybe to persevere or to spend a bit more time on it. And so if we go by that, I think they're 1.3 times, the game-only group is 1.3 times more likely to drop out on this particular level. And again, because we've used a couple of these different methods to kind of look at this data, we get this idea that maybe there's either a problem with this problem or this level, or perhaps this is a place where one of those differences between the groups is starting to show up. So the way we decide to approach this problem is this kind of relates a little bit to the keynote this morning, where now we kind of have to come up with some different methods of evaluation, some different methods of visualization for data that's not, that we can't form up into kind of a traditional evaluation like we could with, survival analysis. And so what we did is we take, we call an interaction network. And so if you remember from earlier, I have this, which is, maybe one student's path or one student's attempt towards solving the problem. And so so we call that, kind of like the interaction line or a solution attempt. And we take these from every student and we put them all together and we make it, so if it's the exact same state, so if the picture is essentially the same, then it'll be weighted. If the edge is the same between two students, then it'll be weighted as well. And we're going to get a pretty large network of these states. This gets us a lot better than staring at an Excel file full of all the different possible states and interactions, but it really doesn't quite get us to a place where you can look at this and say that we know what's going on. Although there is a decent amount of structure, we've kind of done the layout in a way that makes that structure visible. But you can see there's kind of groupings of certain sets of states. And so what we do is we apply a method of clustering, we'll call it community clustering, but community not in the sense that you're thinking of, not in the social sense, in order to kind of consolidate some of these areas where things are really close. And what that allows us to do is turn this larger thing, and this is even filtered a little bit, into something that looks more like this. And so a lot of those kind of groupings, the kind of little ball shapes that you saw before, are now simplified into really just a description of the most common thing that students are doing inside of that area of the map. And so we call this kind of an approach map. And so you can kind of think of it as like high-level strategies of the behaviors that students are doing. And we've kind of labeled this one region as confusion region. And the idea, or the reason that is because once students kind of wander into that area of any of these steps, they're actually very unlikely to make it back out. So essentially, this is a place where students go and they don't return. And sometimes they just restart the problem, and we kind of consider that as an exit and a restart. And it turns out that ends up being pretty important. So this is average number of moves between the two groups. And so, I mean, for the most part, I don't know why I have that as a line graph, but for the most part, you can see that things are relatively the same. And so there's not really a difference in the average number of moves for the students. But we want to get into, there's multiple types of errors that people could be making. So some of these errors are important and some of them are less important. So you can imagine some of the elements are directly related to slope or law of reflection. And some of them might just be a puzzle element. And so using that terminology, we call something a puzzle error if it's not directly related to the learning concepts. So in this idea, there might be like some blocks that are kind of causing you not to be able to make it to the laser area that you need to for the goal. Or it might be that your solution, you've put like your mirror down in a place where it blocks your own path. And then the other types is going to be move and rotation errors. And so the move and rotation errors are ones that are more directly related to the concept. And I think there could be an argument that that even those other ones with the blocking are related to the concept, but they're not as directly related. And so we're able to automatically assign move and rotate errors by using the observed sets of solutions. So essentially, if we see that you're in a state and no one has ever solved the problem from that state, or none of the mirrors in the state are in the right configuration of a known good state, then we can kind of automatically assess that it's a move or a rotate error. So that allows us to know, okay, well, they put this position down wrong, or they rotated the mirror wrong for this problem. For puzzle errors, these are more challenging, And I think that we, maybe in the future we'll be able to do this automatically based on some of the entry points to the clusters I showed you before. But for this work, what we did is we had those annotated. So by looking at the simplified version of the graph, the developers of the game were able to say, okay, well, these are the things, these are the positions that we consider to be puzzle errors, and then we assign that back to the problem. And so by doing that, we can get a different view of what's going on inside of the game. So instead of just looking at total number of moves as a count, we can actually look at the differences in the types of errors. And we can kind of see like there's some approaching some differences, but definitely certain problems have a lot more puzzle errors. And we can see that one of the largest area, or almost the largest, is going to be, is this one problem over here that we see, 1033, and then there's another one which is the 21, the one that we're kind of interested in. And we can see that there's a difference in, and it's very slight, but there's a difference in between the two groups. So if we look at now the average attempts per level, so again, like I said, if someone maybe wandered into that region of confusion, they might exit, they might reset the problem. And so we can see that the bridging group is much more likely to reset that problem. So in that sense, kind of maybe they're actually failing on that problem more often than the game group, but they notice that they're failing, I guess, and reset the problem. And that's a behavior that we see showing up more often for the bridging group than the game group, which is pretty interesting, I think. And the difference between those is significant. We used a t-test just to look at that one area. So this one problem has way more actions than any of the other problems, but we can see that that restarting frequency is something that's pretty interesting. Why would so something about doing the bridging lectures, or bridging part of the content, has made students more likely to maybe be able to do some evaluative processes and see, oh, okay, I need to restart here. Another thing that we did, and this is again based off of kind of our network representation, is something that we call it's based on the good Turing estimation. And so what we're doing here is essentially, this is going to be a measure of how often states overlap. So by that we mean if I have a new student, how many of their paths or their actions that they do, how many of those are going to overlap with something that we've already seen before in the past. And in a way, this gives us a measure of the parts of the network that we have not observed. And so it's a pretty neat little trick that Turing and Good came up with to help with cryptography. But the big thing here is when we look at the difference between certain puzzles or certain levels and other levels, we see that 1021 has a greater amount of diversity. So we've seen less of the overall network. Gives us an idea that that network itself is actually a lot larger than what we've seen. And so overall, what we can say is there are more diverse states in this problem than other places. And so if you imagine if it's a really tough problem, or if there's a lot of areas to wander or get stuck, then that means there'll be more unique states because the students start kind of randomly going. And that, in a sense, is maybe something we could use to talk about the difficulty of puzzles. And so, like I said, to sum it all up, for 1021, players are making more actions. The actions are less consistent. And then the groups, or the students from the bridging group, are restarting the problem more often. And again, this is just what that level ends up looking like. And some of the areas that we've definitely noticed just from looking at it visually, if we try to figure out where are problems happening, it's in the relation of when you're putting down the mirrors. A lot of times the first solution that students will do, they place the mirror in a location where when they get to the end, it's going to block and stop them from actually being able to complete the puzzle. And so you wouldn't actually see that until you've actually gone quite a ways in there and completed it. Some students get to that point and then try really hard to make it work anyway, and some students either restart or reconfigure correctly. But there's definitely a decent amount of place where people do that. Is this just for how much time do I have for questions? Or?
You've got 5 minutes for questions.
5 minutes for questions? Okay. So the very last thing is we did do a flow survey, or what we call a flow survey. So we were just looking at differences between the skill and challenge. Scores were not terribly different between the two groups, but we did notice that there was some difference in perceived learning between the two groups, as well as perceived challenge. So people that were in the game-only group tended to rate themselves higher at their skill, and kind of treated and said that the game was easier than students who were in the bridge group. And so we're wondering if there's a bit of an effect of, if you're only looking at it as a game, then you might evaluate it differently because you don't necessarily see the face value, or you don't see the value of actually what it is that you're learning, because no one told you, hey, this might help you learn. And so there's people in that one group, even though there's no real proof that they're doing better in that game group, that their scores or anything were higher, they quit earlier and they say that the game wasn't very challenging and that they know a lot. And then students in the bridging group would rate that they didn't know as much, which maybe it's a matter of being able to evaluate how much they know or don't know. So we were able to identify some problem spots in these levels. We were able to use some variety of different visualization techniques based on networks in order to figure out where those happen and what they look like. And we're able to give that feedback to the people who develop the game, which can help maybe with future iterations. And the bridge group was more willing to abandon those failed approaches, which I take as they are able to look at the screen and evaluate where they are, and then say, oh, I must have messed up, so I'll restart. And maybe that's partly because of the way that it was connected to those concepts in the course. So I'll take questions with all the remaining time that I've got. Yeah.
So we've probably got time for a couple of questions, if people have got questions.
There was a small difference in the graph that I noticed for the time and the levels for the extinction curve there.
Yeah.
And the time seemed to be different, like right away for the two groups. And the levels that they got to seemed not to be different. It looks like one group is like reliably taking more time early. Is that something that you guys noticed, or something weird?
I'm not sure. I'll have to go back and look. And some of these didn't translate very well. We use a visualization tool to put together some of the images.
That one.
Yeah.
They're staying together.
Yeah.
The one with the time, they separate.
Yeah. So what's happening here is some of the levels take more time than others, and so a lot of the very early levels take almost no time. And so, there's just not a chance, I guess, for dropout to have happened yet. If the first 10 levels only take 10 minutes total to complete, then everyone would stay together. And if the next one takes 30 minutes, then that's when you would start to see the breakdown happen. So in this case, we start to see just that, the time, that's the reason. It's because there's time differences are per problem. Yes?
So actually, it seems that you are talking about serious games. So in serious game, we expect the learners, after playing some game, will learn some concepts, learn some skills. So I'd like to know if you have tried any studies, try to work out whether the learners, after playing the games, learn something.
Yes. And so I failed to mention that this is one of the works that's being based on this data. In this case, we focused on figuring out the problem areas and some of the visualization techniques. But there's a separate work, I think, submitted to EDM this year, where more was looked at the learning gains or the learning differences from a pre-test to a post-test. In this case, we didn't have the data yet for doing that, but also that was already kind of set up as a separate thing was to evaluate that. And in the case of for the results of that, I guess for a spoiler, rather than wait for EDM, there were not huge differences in the learning between the two groups, but there were differences based on the types of errors that people made. So those having more puzzle errors versus having the science content errors ended up being really important. So it turned out that your puzzle errors, those ones that were designated as not relevant to the learning, have no relationship to the changes for pre-test to post-test, while the numbers of science errors do. And that's all I can remember at the moment. But we didn't see like the game groups got this amount more learning compared to the other group. It wasn't something that came up. And I believe a lot of it is because of confounders such as the differences in dropout and some other things.
Right. So if you've got further questions here, there are things you can follow up in the breaks, I'm afraid.
Yeah.
So let's just thank Michael very much for his presentation.
Thank you.